Hi, everybody. So now we're going to look at a particular class of groups known as cyclic groups, which are in some sense the simplest types of groups that there are. And so we're going to study them and get a good grip on them so that we can use our understanding of cyclic groups to look at more complicated examples of groups. So what's the most fundamental example of a cyclic group? Well, maybe the simplest example of a cyclic group is the group of integers with addition as the operation. And the point about the integers is that if you start basically with the number 1 and you start adding it to itself, you get 1 and then 2 and then 3 and then so forth. And then if you take the number 1 and you take its additive inverse, -1, and you start adding it to itself, and then you take 1 and its additive inverse and you add them together and you get 0. And altogether, this process of starting with 1, adding it to itself over and over again, taking its additive inverse and adding that to itself over and over again, and then adding it and its additive inverse together, all of those operations produce all of the integers. So in some sense, if you have a group with the integers and you start with 1, everything else in the group of integers can be made out of 1, either by adding 1 to itself or taking the additive inverse of 1 or adding positive and negative integers together. And so in this situation, we say that the number 1 generates the group of integers. Now, incidentally, just as a side remark, the number -1 also generates the integers, because if you start with -1 and add it to itself a bunch of times, and also take the additive inverse of -1 and get 1, and then add it to itself a bunch of times, and then add -1 and 1 together, you get 0. So that's all of the integers come up that way. So it's also true that -1 generates the integers. But 2 doesn't generate the integers, because if you start with 2 and add it to itself and take its additive inverse and so forth, you're only ever going to produce even numbers. You're never going to get the odd numbers. And so 2 does not generate the integers. And this phenomenon of having a group where you can make everything from starting with a particular element, if you have a group with that property, it's called a cyclic group. And we'll make that more precise in a minute. So here's another example. Our example of the integers mod n, and just for concreteness, let's take n equals 12. And if we think about the integers mod 12, let's put 0 here. We're going to think about the clock. If we start with 1 and we start adding it to itself, then we're going to get all of these integers, and then finally when we take, because 11 plus 1 is 12, which is congruent to 0 in Z12, we see that if we, just by starting with 1 and adding it to itself a bunch of times, we eventually produce all of Z12. So whereas in the, and in particular, we also get the additive inverses here because, for instance, the additive inverse of 1 is 11 and the additive inverse of 2 is 10. So here, again, it's the case that there's a single element, namely 1, and if we add it to itself over and over again and also take its additive inverse, add that to itself over and over again, and then combine the 1 and its additive inverse to get 0, we can produce all of Z12. Although in this case, we don't even really need to do quite so much. We can just take 1 and add it to itself a bunch of times, and eventually we're going to get every element of Z12. And you can see why a group like this is called cyclic, because you start with 1 and you go all the way around the circle and you come back to the beginning. So that's kind of the idea of being a cyclic group, although as we saw, the integers also have this property and they don't really loop back on themselves, but they're still generated by one element, and so they're considered cyclic. And of course, we could, if you want, look at another example. For instance, Z5, it has the same property that if you start with 1, 2, 3, 4, and then after 4 plus 1, you go back to 0, and you get another cycle. And so also 1 generates Z5. So these are 2 examples of what are called cyclic groups, well, or 2 classes of examples. And now we can make a formal definition of what it means for an element to generate a group and what it means for a group to be cyclic. So our definition goes as follows. Suppose G is a group and choose an element from G. And now I want to define this thing, angle G. And what it is it's the set of powers of this particular element for all integer powers. And that set turns out to be a subgroup. We'll prove that later. And it's called the cyclic subgroup of G, generated by, and this should be little g. And I should just say, so for example, in the case of Z5, 1, the group generated by 1, is the set. Well, we're supposed to take 1, and now in this case we're not writing a group operation like multiplication, but by addition. So instead of taking g to the n, we take n times g, which means g added to itself n times. So 2, 3, 4, and then 5, which is 0. And if we keep doing it, we're going to come back to the beginning. So Z5 is the set 1 in Z5 is all of Z5. And in the case of the integers, well, 1 is the set. And you notice now that we're supposed to take n in Z. And in the case of Z5, it didn't matter. We could just take 1, 2, 3, 4, 5. But in the case of the integers, it does matter. We're supposed to take 1, 2, 3, 4. This is 1 times 1, 2 times 1, and so forth. But we're also supposed to take minus 1 times 1, minus 2 times 1, and so on, which is minus 1, minus 2, and so forth. And we're supposed to take 0 times 1, which is 0. And so again, we see that the subset generated by 1 is all of the integers. But if we are in the integer z and we take the subset generated by 2, well, that's 2, 4, 6, and then minus 2, minus 4, minus 6, and then finally 0, because you take 0 times 2 as well. And that is not equal to z. So in the particular case in which we can choose an element of the group so that this subset generated by the element is the entire group, then we say that G is a cyclic group generated by the element little g. So we just have to prove the existence of a generator. It's not the case that every element is going to be a generator. So we see from this that Z5 and Z are cyclic groups. And actually, Zn for any n is cyclic, because if you start with 1 and you go 1, 2, 3, 4, 5, 6, dot, 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 all the way around to n minus 1, and then you add 1 again, you get back to n, Zn is also cyclic, and all of these groups are generated by 1. So let's look at a few more examples. I've already talked about Z and Zn. And I mentioned that the group 2, the subset 2 in Z, consists of the even numbers. But you could choose any n. For example, you could take 5. This is the multiples of 5. So it's 5, 10, 15, but also minus 5, minus 10, minus 15, and also 0. And maybe I'll just point out that this is a subgroup. We'll see this in general later, because remember, we have to use our subgroup theorem. To tell if a subset is a subgroup, we need to check that if, first of all, that it's non-empty, which it clearly is. And then we have to check that if A is in 5 and B is in the group generated by 5, then A minus B is in the group generated by 5. And that's just the statement that if A is equal to 5 times n and B is equal to 5 times m, because A is just the set of multiples of 5, then A minus B is 5 times n minus m, which is also in the subset generated by 5 because n minus m is an integer. And maybe one more example, if you remember the group of symmetries of the equilateral triangle, there were 6 symmetries. There was the identity symmetry, the rotation, and the left rotation and the right rotation, which could be thought of as 1 rotation and 2 rotations. And then finally, there were the 3 reflections. Corresponding to whether you fixed A and reflected around B and C, fixed B and reflected around A and C, or fixed C and reflected around A and B. And if you take the subgroup just generated by R1, well, that's got in it R1, R1 squared, which is what you get if you rotate twice, and then R1 cubed, but if you rotate the triangle 3 times, you get back to the identity. And then if you keep going to the 4th or to the 5th or whatever, you're just going to go around and around and around. No matter how many times you do these rotations, there's really only 3 different ones. And also, if you go backwards, R inverse is R squared, and R to the minus 2 is R. You can, that's because as always, R cubed is the identity. So if you rotate backwards, that's the same as rotating forward twice. So the cyclic subgroup generated by the rotation has 3 elements in it, and so it's a subgroup. In this symmetry group, which has 6 elements. So what we've shown here is that this particular element R doesn't generate the full group of rotations. It just generates the full group of symmetries. It only generates the subgroup of rotations. A few more examples. Well, if instead of taking the rotation, we just picked one of the reflections, let's say the reflection which fixes A. Then our subgroup generated by S contains S and S squared, but S squared is the identity, because if you do this reflection twice, it comes back, and that's all there is. So the cyclic subgroup generated by S has 2 elements. Another example, U of 7. So remember what U of 7 is. U of 7 is the collection of A in Z7 such that the greatest common divisor of A and 7 is equal to 1 with the operation multiplication. And since 7 is a prime number, to have no factor in common with 7, U of 7 is just the collection 1, 2, 3, 4, 5, and 6. Those are supposed to be congruence classes, but I'm not writing the brackets. So there's 6 elements. Basically, it's Z mod 7 without 0. And if you take 2 and you start you take 3 and you start looking at its powers, you get 3 squared, which is 2, 3 cubed, which is 3 times 2, which is 6, 3 to the 4th, which is 3 times 3 cubed, which is 3 times 6, which is 18, which is 4, because we're working mod 7. And then 3 to the 5th is 3 times 4, which is 12, which is 5, mod 7. And finally, 3 times 5, which is 15, which is 1, mod 7. So we see that the powers of 3 give us every element of U of 7. In particular, the group generated by 3 is equal to U of 7, so U of 7 is cyclic. Just to sort of round this out, it's the case that to be cyclic, a group has to have more than one generator, but may have more than one generator. But to be cyclic, it only needs one generator. Let's look at the case of Z12. So we already know that if you take 1, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 0, which is all of Z12. And so we know that Z12 is cyclic. If we take 2, the group generated by 2, we get 2, 4, 6, 8, 10, and then 12, which is 0. And if we keep going, we're going to get 2, 4, 6, 8, 10, 0, 2, 4, 6, 8, 10, 0. So this is smaller than Z12. If we take 3, we get 3, 6, 9, 0. If we take 4, we get 4, 8, 0. If we take 5, you get 5, 10, 15, which is 3, 8, 13, which is 1, 6, 11, 16, which is 4, 9, 14, which is 2, 7, and then 12, which is 0. And if you count these up, you see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we found that Z12 has another generator. It's not just generated by 1, it's also generated by 5. And as just some concluding remarks, I want to emphasize that not every group is cyclic. So let's look at some examples. So not every group is cyclic. And that's, first of all, we know that the symmetries of the triangle are not cyclic. And how do we know that? Well, remember what we know. We know that the elements are either rotations, and they give you 3 elements, or reflections. They give you 2 elements, or the identity. The identity element generates just a group with 1 element, namely the identity element itself. So none of the elements of the symmetry group of a triangle give you the full 6 element subgroup, 6-element group of symmetries of a triangle. So we know that there's no generator, and so the symmetries of the triangle are not cyclic. What about another example of a group which isn't cyclic is the Quaternion group. Let me just remind you what the Quaternion group is. It has 8 elements, plus or minus 1, plus or minus I, plus or minus j, plus or minus k. And the multiplication rules are that I squared is j squared is k squared is minus 1. ij is k, but ji is minus k. jk is I, but kj is minus I. And ki is j, but ik is minus j. And how do we know this isn't cyclic? Well, let's just test every possibility. The group generated by 1 only contains 1. The group generated by minus 1, well, it contains minus 1 and also minus 1 squared, which is 1, but then no matter how many more powers you take of minus 1, it only goes minus 1, 1, minus 1, 1, minus 1, 1. If you take any of the other ones, I, j, or k, let's call that alpha. So for the sake of argument, let's just look at I. Well, we have I squared, which is minus 1. We have I cubed, which is minus I. And then we have I to the 4th, which is 1. And that has 4 elements. And you can see that also j and k also have 4 elements. So none of the elements of Q are enough, give you powers which fill out all of the Quaternion group. So the Quaternion group is also an example of a group which isn't cyclic. And in some sense, you could say most groups aren't cyclic, but the cyclic ones are particularly simple, and so they give us a place to begin to study things that are happening in more general groups.